Well, here we are again. This is the Physics 2A video lecture. It is the Physics 2A video lecture 9, and it's more of the review session before the exam. Right? The exam is Thursday, 5 to 7 p.m. for the one section, and Friday, 8 to 10 a.m. for the other section. And you're going to receive the exam by email, and then take the exam and get it back to me by email as well. So that's how that's going to work. Chapters 6, 7, 8, and 9, and I did the review of chapter 6 the other day. So this session I'm going to review chapters 7, 8, and 9. And anything else to say? Well, I will send an email off soon after I post this lecture to YouTube and give a little more heads up. But then after that, you'll hear from me next on the exam date itself. Good. What else? I think I said last time the lecture notes for these exams, exam 8 and 9 from this week, those lecture notes are also due on Friday in a separate email, of course. The exam, has to be its own email. Good, so let's have a look at chapter 7. What we were talking about in chapter 7. So what I'm focusing on here is circular motion and gravity. The rotational motion formalism I'll talk about in connection with chapter 8. Okay? So circular motion and gravity. At this point, we've had some good examples. The lab, the video lab or whatever, the online lab, I thought it was a very nice demonstration actually. And the current lab that people are doing is buoyancy, and it's also very relevant for our exam, right? Because it's out of chapter 9. Good, so circular motion and gravity. So to begin with, the circular motion formalism, I'm leaving off the word uniform. We're actually talking about uniform circular motion with a constant speed. So we have a circle here of radius r, and we've got some object going here, let's say counterclockwise, doesn't really matter. And the speed is equal to the distance over the time. So we often use this formula, 2 pi radius over capital T, which is the period, it's the time it takes to do one's circumnavigation, as it were. Yeah, so the speed may very well be constant, when we're talking about uniform circular motion, but the acceleration is not constant. The acceleration is changing its direction all the time because it's always pointing towards the center. So that's the centripetal acceleration, and that's the other important formula here. The centripetal acceleration, a sub c, is v squared divided by r, always directed towards the center. So that's part of your formula sheet as well. Okay, 2 pi r over t, centripetal acceleration. Yeah, speaking of the exam, since the exam's being taken at home, it's not closed notes, right? Okay, it's open notes and everything. So I don't necessarily have to give you guys a formula sheet. You have to be collecting the relevant formulas now. The main thing about the exam is it's 2 hours, and it's got to be done in 2 hours and sent back to me. Okay, otherwise it's very similar to everything we've been doing. It's similar to the previous exam, so there's no surprises in that regard. Good, so here are 2 formulas. And some examples I'm going to do right away, just using this. Just the simple circular motion would be 1, and I could talk about this, namely anywhere we're going in this circle, the acceleration is always directed towards the center. Down here it's directed towards the center. And of course we have centripetal force is mass times centripetal acceleration. So that's just Newton's law. So the quiz I did well, not everybody's in my lab section. Yeah, I sent out a quiz that was basically like the lab activity with the circle, with the ball that was going in a circle. Okay. So that of course is a very, very important example. In fact, you all go ahead and draw that. You've got this ball going in a circle. There's the string, and then somehow, you know, if I do it through a central force table, it's on the table. Otherwise, it's somehow being directed through that hole there. And so you've got a force here, mg. This little guy, m, is moving around. And so the centripetal force on this one here, as it whirls around in a circle, we have that centripetal force mv squared over r. There's the radius of its orbit, right? But the force is being supplied by the vertical mass, so that was m times g. So you can work your way through that. Now the next example I want to give is one we did in class. Did we do that in class in a video lecture? The roller coaster. Okay. Roller coaster is a very important example. So we've got the roller coaster with its hills here. And then if you're at the bottom of the hill, you're in a certain radius of curvature, point A, r sub A, and then you have n mg. Then your Newton's law is n minus mg equals mv squared over r sub A. Okay. This is the net force equals the mass times the centripetal acceleration. If you're on top of the hill, you actually have the same free body diagram, but your positive direction is down, so you actually have to reverse the order of these, and you get an interesting result that is somewhat different. Okay. So we wanted to know the roller coaster. Okay. Want to know the roller coaster. Another example, and you know the next example I'm going to give is the pendulum, and we'll see it's identical to the roller coaster. So how about if I leave the roller coaster up here and remind us of the pendulum. So roller coaster, another example, pendulum. Here the idea is that we release this pendulum, say from this point up here, and it swings through in an arc. Of course, it's moving fast down here. And at that instant in time, down here at the bottom, we are going to have in this case, tension. Got to use the letter T, got to know the context, right? It's not a period, it's a tension. We've got the tension, and we've got the weight. And so our formula is tension minus mg for Newton's law. Left side equals mv squared. And how about I say L instead of R, because the string is of length L. But of course it's playing the role of the radius. And this equation here is identical to this one here. Okay, so it's the same problem. So definitely be able to do the roller coaster and the pendulum, and the point is you have to set them up, and from there, you know, you're good to go. What if instead of releasing it from up here, I had released the pendulum from down here, okay? Midway, release it from midway, what's the difference? Actually the same construction here, it's gonna be going slower. The speed that this thing has, you need that V, the speed that it has is going to come from the height difference that it had. You would use your energy conservation to find that speed. No problem. Good, so there's an example. Get your roller coaster, get the pendulum. So that's circular motion. Now I want to talk about gravity. Newtonian gravity. And then, I give the Newtonian gravity formulas, and then we go to circular orbits. Good, so now gravity. There we have Newton's law of gravity. M1, M2, two particles in space separated by a distance r. They experience an attractive force towards each other, along the line joining them, and the force is proportional to the universal gravitational constant. The product of the masses inversely proportional to the separation distance squared. Okay, the celebrated inverse square law of Isaac Newton, right there. Okay, and this r doesn't have to be the radius of a circle at all. Right now it's just the separation distance. But of course when we get into orbits, that's what it'll be. It'll be a radius. So there's the force, and this constant g is a little tricky. We're not using calculators, and I'm making the exam regardless of whether you have a calculator at home or not. You're not going to need one, right? The way I might write our exam is there's no need for a calculator. So if we needed to know anything about capital G here, the example would be the following. Put ourselves on Earth of radius capital R. There we are. Earth has its large mass. I can express this formula here as F is equal to G, mass of Earth, our own little mass divided by the radius of Earth squared. That's the force attracting me to the center of the Earth. It works for spheres to sphere, okay? Well, this is also, since that force there, the Earth attracts me with that force, that's just my weight. So that's mg like this. So this little g, that's our 9.8 meters per second squared. In an exam situation, we can use 10, right? Keep things simple. So what we learn here is that this g, I'll leave it on this side here. Cancel m on both sides. We get capital G m over radius squared. So this is a great formula. I think I recommended that you guys look these numbers up and plug them in sometime and see that they really give you 9.8. But this substitution is something to keep in mind if I ask you to express certain results in terms of lowercase g. I can do that with certain orbital type of problems, and this is a very nice basic identity for our Earth. This is just free fall acceleration as we learned a long time ago, and this is Newton's gravitational constant, the mass of Earth, radius of Earth squared. Okay, next I want to talk about circular orbits. So when we set up a circular orbit using Newtonian gravity, here we'll say circular orbit, then it's Newton's law like this. F equals ma. Always write that down for orientation. Then we have, let's say, a circular orbit around a central body. That way, instead of the subscripts, I use the capital M and the little m. So there's my force. And on the right side, I have m v squared over r because it's a circular orbit and centripetal acceleration. Right away, you can cancel m's here. You can solve for v if you want. And so this is one type of problem that we've done. Another type of problem is to equate this left side with this expression where we write the m over r and we express the speed in that form that I had there in the race. Okay. So now if I identify, equate the left side here and the right side here, still get the cancellation of the mass, but now we can express distances, radii, and times. Okay, so this is the one. These two types of problems. Actually, there's one problem here. You set it up here, and you can express it in a couple different ways. Okay. So those would be our circular orbits, and the information we can get from those. Now, in gravity, we also have energy and conservation of energy, very important topic. And here, let's go ahead and leave Newton's law up. In this particular type of gravity, I wasn't able to do any real derivation. Okay, we didn't do an integration, so I just gave us the form of the potential energy. So when we're doing energy, the potential energy that goes with this formula, capital U is the potential energy, it's minus the product of the masses in G, could also be done with M1 and M2, right? Divided by 1 power of R, and it has to have this minus sign. Okay. Very important that it has that minus sign. And then, of course, we can do these kind of energy at A equals energy at B. Well, here's our central body. Here's point A. Here's point B. Maybe we're blasting off into some kind of orbit. Maybe we're blasting off straight up and down. Okay, there's the central body, radius R, capital M. And here's the orbit that we would be occupying. Okay, so for us, conservation of energy is always E sub A equals E sub B. And at point A, whether or not we were moving down here, our energy, well, first I'm going to separate that off. M E sub A squared minus G over R sub A. So you want to remember how to write this formula down. Energy, right? I'm writing the kinetic energy plus the potential energy. But the potential energy has its minus sign, okay? This is kinetic plus potential, but it has its minus sign. So you write it down this way, and now you have one equation you can solve for one unknown. So what were some of the important examples here? Escape speed, that one was interesting and very important. So escape speed, and what that meant was we're blasting off with some really high speed here on the surface of Earth. So that would be the speed v sub A. But we have this potential energy on the surface of Earth, so that would be the radius of Earth. Then, instead of going up and falling back down again, it's going out to infinity. And when it gets to infinity, it can stop. So when it gets to infinity, it stops, so v sub B, where now B is not right here, but then infinity, v sub B is equal to 0, and R sub B is equal to infinity, and 1 over infinity is also 0. So for the escape speed problem, we ended up with 1/2 m v escape, I'll give a little subscript e squared, minus g m over the radius of our central body was equal to 0, and then you could go ahead and solve for the escape speed. You can memorize it too if you want, but it's more important you recognize how to get that speed. So any of the energy problems that I assign you in Newtonian gravity would involve setting up this equation. This one's very important. And you set up the equation, right, nothing can go wrong. You've gotten part way there. Now, another question that I like to ask is, how much energy does it take to get from one orbit to another? How much energy does it take to get from a lower orbit to a higher orbit? And that would be the difference of their respective energies. So let's go ahead and write this one down. Energy required to go from orbit R sub A to orbit R sub B. That would be delta E, would be that final energy, I'll call it E sub B minus E sub A. So actually we would have the equation I had just written up there a moment ago, and we would take its difference. Not quite. Let's go ahead and do this. Okay, so how about we draw these orbits? I could take a near-Earth orbit, and I can take an orbit that is twice the radius of the near-Earth orbit. Okay? So we have these two orbits there, and one of them is the A and the other one is the B orbit. Okay? So E sub A is equal to 1/2 m B sub A squared minus G m over R. Because since it's a near Earth orbit, we can identify the orbital radius with the radius of the Earth. And E sub B is equal to 1/2 m B sub B squared minus G m over 2 times R. So now I'd have to take the difference of those two. These difference between these isn't going to give us any problem, but how do we know what V sub A and V sub B are? What are these orbital speeds, V sub A and V sub B? So I'll just write orbital speeds using Newton's law of gravity. So I have to go back to G n m over R equals m V sub A squared, sorry, R squared, A squared over R. So I had to actually set up this equation in order to get V sub A. And if I set up this equation for 2R, I would get the V sub B by the same token. But one thing I'll warn you, if you set up this equation for 2 times R, then you have to have, here, I'll just write it here. You have to have 2R quantity squared, okay, which would be 4 times R squared. 4 times R squared. Okay, so that's the type of thing we can think of doing on the Newtonian gravity type problem. Okay, let's see how much time we've spent so far. Yeah, time flies. Okay, let's move into chapter 8, which has so much going on, but here we go. So for chapter 8, we'll be talking about rotational motion, torque, and Newton's law for rotating objects. So I'll put these down. Chapter 8. In fact, let's start with the static stuff first, because I definitely want us to be able to do a couple statics problems. So, torque and equilibrium. We did a lab on this with the rulers, so very important. Good, so the equilibrium conditions, let me just draw a couple of examples of increasing difficulty. So the first example is our ruler balanced on the pin. And say we hang a mass from here, and say the ruler has a different mass, so I just use different letters, upper and lower case. So how does this thing balance out? Here we know that at the center of mass, even though there's nothing marking it, the center of mass of this uniform stick is where the weight actually acts. And so if I have this unknown x and the entire ruler of length capital L, my equilibrium condition is going to be mg times x minus mg times L over 2 minus x equals 0. So I just set up my torque equilibrium condition. Okay, that one we've done numerous times. That's pretty elementary. Elementary, but you'd be surprised when you encounter it on an exam. But there you have it. Okay. This was a counterclockwise torque, this was a clockwise torque. The L over 2 because the entire string was of length L. So the distance L over 2 minus x is this one here that I'm drawing right now. Okay, that's our L over 2, half the length minus that x. Okay, how about another example? Another example, and this one is in our notes, we've done it, is if we just have a rod with a sign or something hanging from it, the famous ice cream problem. Okay. And of course that bar there is going to bend unless you guy it up with a wire here. And then we start to have some kind of mg. I'll even write m plus m times g, because I made the ice cream sign and the bar, the same length on this one. So I don't have to worry about the different centers of mass. Then I have a tension pointing in that direction, T, and angle theta. I had forces at the wall, reaction forces, and my equilibrium conditions for this problem allowed me to find, say, the unknown tension given everything else. Okay? So you want to be able to set up the slightly more complicated equilibrium problems. So I just write here example, and the more general example from the lab, when we had the ruler, there was the axis pin, and we had this one going over a pulley and some mystery mass here. Okay, that one was surprisingly difficult. A simpler version would not even have any extra hanging masses from it. Okay, a simpler version would be this problem right here. Star, that's always my center of mass, right? And here's some mass. Maybe the ruler has another mass. Okay. Maybe we have an angle. Therefore, there is a reaction force at the pin. One in R and one in X and one in Y direction. And now we would have, given also a length of this ruler, type of problem we could set equilibrium conditions for. So yeah, those are the type of equilibrium condition problems. And yeah, I have a couple in mind. We'll see what I actually put on there. But as always, you have to draw it carefully, label the forces, and then let the problem take you where it does. None of these are the type where you can just look at it and guess the answer. You got to take it step by step, and of course we're getting a lot of partial credit, so you want to just show every step you took. Okay. What else do we have here? Now we're going to move into the rotational motion part of this. So this was the equilibrium. For the rotational motion, we first of all have this formalism that completely follows the linear formalism. So I'll just remind us, we have theta where this is an initial angle for the position, the initial angular velocity, the angular acceleration. So these kinematic formulas can come in handy if you're just wanting to do a problem of rotational motion. We have to be aware of these also because when we're doing rotational dynamics, so this was just the kinematics, doing rotational dynamics, we have, for Newton's law, I'll put Newton here, instead of F equals ma, we have torque equals I alpha. Moment of inertia. We want to be comfortable recognizing a couple of moments of inertia. This one here, just a point particle itself, say going in a circle. So the point particle going in a circle has mr squared. Okay. If we have a hoop of radius r, it's also mr squared. This is for a solid hoop of radius r. If we have a disk, we have 1/2 mr squared. That would be a disk or a cylinder rotating about its axis. Cylinder as well, it would be the same thing, 1/2 mr squared. So those are what take the place of the mass, so to speak. That's the inertial term in this torque equals I alpha expression. We also have the kinetic energy of rotation is 1/2 I omega squared, just as kinetic energy translation is 1/2 mv squared. Okay, so we have those full analogies in this subject here. And in order to incorporate rotation and translation, we had to be able to use the translational speed is omega times the radius. Translational acceleration is alpha times the radius. For the exam, you could be assembling these kind of formula sheets just so you have them when you need them. Okay. Or we can look them up at the time, whatever works best. So those are the aspects of the formalism. And now what kind of problems would we be talking about? Let me just draw your attention to the rolling race, which is in our notes. Okay, the rolling race is an interesting one. And the unwinding spool what will I call it? The spool and the bucket, I think is what we could call it. Remember, we had the picture of the spool that's unwinding. There's a bucket. There's the handle. There's a bucket unwinding. So the spool and the bucket would be interesting as well. What else do I have in here? Too many good things. Let's see. Let's see how much time we have left. Okay, we're doing fine. Okay, I'm going to, should I do one more of these problems or maybe move into chapter 9? I'm going to move into chapter 9. This last one, and we have a nice lab going on this week as well. It's going to be helpful, I think. In fact, I should study it and maybe use that. It's a nice lab. Okay, chapter 9 is fluids. And other stuff as well. We'll just call it fluids here. So first of all, we have to remember our new concepts. We have density, mass per volume, and we also use this same definition to express mass as density times volume. Very handy. I remember I did something in one of my video lectures with this right here. We have pressure, P equals force per area. The unit is the Pascal, and we also often use force equals pressure times area equivalently. So those were those definitions. And then we had the atmospheric pressure. So let's see. Then we had the pressure depth formula. I feel like I'm repeating a lecture I gave before, but that's all right. P equals P0 plus rho GH. The atmospheric pressure 1.01 times 10 to the 5 Pascal. We had a nice demonstration of that. And the barometer. So the barometer again, you filled this capillary with some fluid, and it turns out it had to be long enough. You upended it in a dish of the same fluid, and that left behind vacuum at the top, and the column of this fluid here is being supported by the atmospheric pressure, which is pressing down right there. So for that reason, we get the atmospheric pressure equals rho GH. Okay. It's this formula here, the pressure. In this case, we're not talking about the atmospheric pressure. There's a vacuum up there with zero pressure, so that pressure is just rho GH. And depending upon the fluid you use, this H is going to take on different values, okay? So if it's mercury, you have the density of mercury, you have a certain height of the column. And if it's some other fluid, if it's red wine or something, it turned out it had to be 10 meters high, or some enormous amount. Okay, so that's actually one of the key applications of this thing to really understand what's going on. The next application is the buoyancy force. So I'll go ahead and erase these and talk about the buoyancy force. Today's lab, or this week's lab, has some interesting stuff regarding the buoyancy force. So the buoyancy force is, in words, it's equal to the weight of the displaced fluid. Now, the weight of a fluid is its mass times the gravitational acceleration. So if we're talking about the weight of the displaced fluid, this is the density of the fluid that something's floating in or immersed in. This is the volume that's been displaced. That's why we say the weight of the displaced fluid. So that's Archimedes' principle right there. Make sure you understand that. Then really the prototypical example that covers a lot of other examples. If you understand this one well, and our lab is on this, without the string by the way, but if you have something more dense than water hanging in water here, and there's a string's got a tension, and we could even measure that tension by hooking it up to a scale, right? It would have so many newtons, okay? I'm just concentrating on the free body diagram of this thing. Let's say it has a mass that we know because we weighed it, and then it's a piece of metal, we dipped it in the water, and now we're weighing it again. Well, it's going to have a smaller reading up here than it did when it was just in air. So now it's F net equals 0 because it's a static problem. We have the mg, okay, and we have the tension, but we also have the buoyancy force. Okay. So we would have F buoyancy plus tension minus mg equals 0. Then we go ahead working on this. Suppose, I'm just going to do another example before I come back to this one. This one I've done several times, right? So I made use of all these things. So we've done this one before. Suppose we have, let's call this another example. Here's the water level, and we have an object here. It's floating, and we put another object on top. That's this week's lab, okay? Got something floating, the styrofoam barge and the aluminum and the wood and so forth, okay? What you want to do is just set up your free body diagram with this thing as well. And here you have to be kind of careful, because let's say we're doing the free body diagram for this big block, which I'll call capital M, and this little one here, I'll call little m. Any reason for that? No. Just want to write it so. Okay, it's a smaller block, but its mass right here. Point is, what are the forces acting on capital M, the big block? The forces acting are mg. Now I'm going to put the buoyancy force up here, or down here, but pointing up, and then I've got this little force here. Well, this is pressing on it with a normal force, okay? But we've done this often enough, we can say, well, it's just pressing on it with mg pointing down, okay? So mg pointing down. So F net equals 0, the force on the big block, there's a buoyancy force, there's minus its own weight, minus the little weight that's on top. Okay. So we set it up the same as this one right here, but we got to be careful with the directions of the arrows. Okay, so this one we've done often enough. I'm going to erase and talk about this one a little bit more. Okay, so I'll erase this one here. So yeah, we're just going to evaluate this buoyancy equation. So once again, and there's our definition, that'll come in handy. So we have the buoyancy minus mg minus lowercase mg. We have the density of the fluid we're in, the volume displaced, so I'm going to write fluid, DISP for displaced, G minus mg minus mg equals 0. Right? There's our equation, and we have to, okay, it'll solve for one thing, one unknown quantity. But we could have a situation where, for example, this thing is half in and half out. So that's an added important point. This volume that's displaced here could conceivably be half of the total volume. So that's something you have to take into account. Okay? So you're just using this simple equation, but you have to take that into account. Yeah, once we set this up, we're pretty much good to go. And you know, one situation could be that this mass presses this one down so that it's fully submerged. Okay. Then we would be able to use this M is equal to density V, okay, if the full thing, and if it were, yeah, okay, we could use that formula, but then this would be the density of the object. Okay, so you want to keep those apart. You've got the density of the fluid, that is for your buoyancy force, the density of the surrounding fluid. You have the density of the object if you want to calculate its weight. They can be different. As simple a problem as an ice cube floating in the water, a block of wood floating in the water, has to make use of those. So there's a heads up. Let's see what else. Archimedes, force table. Well, I think since we're coming on the 50-minute mark, I think that's as far as we're going to go. We've had two 50-minute or 45-minute lectures this week, and these are both for the Tuesday, Thursday, and the Monday, Wednesday, Friday group. And what I'll do is I'll just make two completely separate exams. Try to make them pretty much the same. And have I missed anything crucial here? Let me put down one more topic. And if I do the Bernoulli's principle problem, which I've demonstrated, Bernoulli and continuity equations, definitely want to have them in your repertoire as well. So continuity equation. That was the streamline idea. You've got nozzles, different cross-sectional areas. So there we had A1, B1 equals A2, B2. So when the thing is skinnier, the speed is higher. When the thing is fatter, the speed is lower. And then we had Bernoulli. Bernoulli's equation looked just like energy conservation. That's because it is energy conservation. There we had P sub 1 half rho V1 squared rho G Y sub 1 is equal to P sub 2 half density V2 squared rho G Y sub 2. Of course, you recognize your kinetic and potential energies. The reason the pressures are in here is because it comes from a work change of energy theorem, so to speak. This one here, we can think of some stream line type of flow that is taking place in a gravitational field, so in a y-axis going up. And then we locate a point 1 and a point 2, and then just set up this equation. So anything we do here would not be too difficult at all. Okay? So make sure you have a handle on this and whatever we talked about in the lecture for that, which was all pretty basic. And that's where we'll leave it. So that's the end of this video lecture 9 and the review. Like I said, the exams are going out Thursday afternoon and Friday morning. You'll have 2 hours to do them, scan them and send them back to me. And I will send out one more email to everybody probably later today or tomorrow, just for a final heads up. So keep taking good notes as always, and see you next time.